Welcome. In this session, we'll explore a fascinating problem titled Maximum Employees to be Invited to a Meeting. We'll break down the problem, analyze different approaches, and work toward an efficient solution. Get ready to dive into an engaging coding challenge. In this problem, you are tasked with inviting the maximum number of employees to a meeting. Each employee is represented by a number from 0 to n1, and they each have a favorite person. This information is provided in the form of an integer array called favorite, where the value at each index represents the favorite person of the corresponding employee. An employee can attend the meeting if they are invited directly or if their favorite person is invited. The goal is to determine the maximum number of employees that can be invited under these conditions. The input includes n, the total number of employees, and the favorite array, where each value is a valid index referring to one of the employees. The output is a single integer representing the maximum possible number of attendees at the meeting. Let's look at an example to understand the problem better. Suppose n equals 5, and the favorite array is 2, 2, 3, 4, 0. In this setup, employee 0's favorite person is employee 2, employee 1's favorite person is also employee 2, and so on. These relationships form a cycle. Employee 0 points to 2, who points to 3, who points to 4, who points back to 0. In this cycle, the longest chain of employees that can be invited without breaking the cycle includes 3 employees. Therefore, the output for this example is 3, as that is the maximum number of people who can attend the meeting. Now let's consider another example. Here, n equals 6, and the favorite array is 2, 2, 3, 4, 5, 0. Employee 0 loves employee 2, employee 1 also loves employee 2, and the chain continues with each employee pointing to the next until employee 5, who loops back to employee 0. This forms a cycle that includes all 6 employees. Since everyone is part of a single cycle, it's possible to invite all 6 employees to the meeting. Therefore, the output is 6, which represents the total number of employees that can attend. Here's another example to illustrate the concept further. In this case, n equals 3, and the favorite array is 1, 2, 0. Employee 0's favorite is employee 1, employee 1's favorite is employee 2, and employee 2's favorite is employee 0. These preferences form a cycle among all 3 employees. 0 points to 1, 1 points to 2, and 2 loops back to 0. Since everyone is part of the same cycle, all 3 employees can be invited. Thus, the output for this example is 3, which is the total number of employees. To solve this problem, it is crucial to analyze the relationships between employees as a directed graph. Each employee points to their favorite person, forming chains and cycles within the graph. Cycles are especially important because all members of a cycle can be invited. Additionally, chains that terminate without forming a cycle must be carefully considered. Edge cases include scenarios where there is only one employee, where all employees form a single cycle, or where there are multiple disjoint cycles or chains. The challenge lies in efficiently analyzing these structures to determine the maximum group size, especially given that n can be as large as 100,000. To tackle the problem, we first consider 2 potential approaches. The brute force approach is the more intuitive starting point. Here, we analyze every possible grouping of employees by following the favorite relationships to determine which groups are valid. A group is considered valid when it forms a cycle or some other structure where all members can attend the meeting together. However, this method becomes computationally expensive very quickly. Since we're iterating through all employees repeatedly, the time complexity grows quadratically, n squared, which becomes impractical for large inputs, especially when the number of employees can reach up to 10,000. A better way to approach this problem is through graph theory. By representing each employee as a node and their favorite relationships as directed edges, we can reduce the problem to analyzing the graph structure. This graph-based approach allows us to focus on identifying cycles, mutual favorite pairs, and chains of employees leading into these structures. Each of these components plays a critical role in determining the maximum group size that can attend the meeting. This strategy is more structured and computationally efficient than brute force, paving the way for an optimal solution. The chosen strategy builds on the graph-based approach and leverages depth-first search, or DFS, to solve the problem efficiently. The first step in this approach is cycle detection. Cycles in the graph represent closed groups of employees where everyone can mutually attend the meeting. Using DFS, we identify these cycles, calculate their sizes, and track the largest cycle size. Next, we address the special case of mutual favorites. These are pairs of employees where each is the favorite of the other. These pairs act as a foundation for larger groups, and we can extend their size by adding chains of employees that lead into them. This ensures that these pairs are maximized as part of the overall solution. Finally, we account for nodes not part of any cycle. For these nodes, we calculate the length of the chain leading into a cycle or a mutual favorite pair. These chain lengths are then added to the corresponding cycle or pair to maximize the group size. This step-by-step strategy ensures that all components of the graph are utilized to their fullest potential. Now, let's highlight some key insights that make this approach work. The first observation is that the problem fundamentally reduces to graph analysis. Cycles and chains in the graph determine the group sizes, and understanding these structures is crucial. Another important insight is that mutual favorite pairs are a special case. These pairs can grow by attaching chains to them, so handling them separately is vital for maximizing the solution. From an efficiency standpoint, depth-first search is a natural choice. It allows us to detect cycles and calculate chain lengths in a single traversal, leading to a linear time complexity of O(n). This makes the solution highly scalable, even for the upper limit of employees. In terms of trade-offs, while the brute force approach is simpler to implement, it's far less efficient. The optimized DFS-based method, on the other hand, is slightly more complex but dramatically faster. Additionally, while DFS is preferred for this problem due to its recursive nature and suitability for cycle detection, BFS could also be considered in other graph problems with different requirements. Finally, the space complexity of the graph-based solution is O(n), which is manageable given the problem constraints. Overall, this approach balances efficiency, scalability, and correctness, making it the ideal choice for solving the problem. In this problem, we are tasked with finding the maximum number of employees who can be invited to a meeting, given a specific relationship structure. Each employee in the company has exactly one favorite employee, which creates a directed graph where nodes represent employees and edges represent their favorite relationships. For instance, if the favorite array is 2, 0, 1, employee 0's favorite is employee 2, employee 1's favorite is employee 0, and employee 2's favorite is employee 1. This structure forms a graph with edges 0-2, 1-0, and 2-1. The goal is to identify the largest group of employees who can attend the meeting, which may include cycles or chains within the graph. To approach this, we model the problem as a directed graph and focus on detecting cycles, as they represent groups where employees exclusively favor one another. Using depth-first search, or DFS, we can systematically explore the graph, detect cycles, and determine their sizes. By marking nodes as visited and tracking the current path using a stack, we can identify if a node revisits itself within the stack, indicating a cycle. Each cycle size then contributes to the potential group size, so recording these sizes is an essential first step in solving the problem. Now, let's delve into chains leading into cycles, as they can extend the size of valid groups. When an employee outside a cycle favors someone within the cycle, they effectively join the group. To handle this, we perform a DFS for each node to calculate the length of chains that lead into cycles. We use an array, chain_length, to store the maximum chain length for each node. Another important case to consider is two-node cycles, such as when employee A favors employee B, and employee B favors employee A. These cycles are unique because chains can lead into both nodes, significantly increasing the group size. To address this, we specifically identify two-node cycles and calculate the combined size of the chains leading into both nodes. Finally, we combine the results to determine the overall maximum group size. This involves comparing the size of the largest cycle with the combined sizes of chains leading into two-node cycles. The key insights here are that cycles represent self-contained groups, and chains leading into these cycles must be carefully tracked to maximize the group size. Two-node cycles are particularly noteworthy because they allow contributions from chains leading into both ends of the cycle. This makes them a critical case to handle, but our approach remains efficient. By using DFS, we ensure that both cycle detection and chain length calculations are performed in linear time relative to the number of nodes, resulting in an overall time complexity of O(n). For data structures, we use a visited array to mark process nodes, a stack to track the current DFS path for cycle detection, and a chain_length array to store the maximum chain contribution for each node. The graph itself can be represented efficiently using either an adjacency list or direct indexing into the favorite array. Each of these data structures requires O(n) space. The algorithm is also robust against edge cases, such as a single-node graph, where there are no cycles, or scenarios where the entire graph forms one large cycle. It can also handle disconnected components, where multiple independent cycles or chains exist within the graph. In cases where chains lead into two-node cycles, it's important to account for contributions from both nodes in the cycle. To implement the algorithm, we begin by iterating over all nodes, performing DFS for those that haven't been visited. The pseudocode starts by defining an input favorite array and initializing necessary data structures, such as the visited array, stack, and chain_length array. The max_group variable keeps track of the largest group size encountered. The DFS function is core to the algorithm. It marks nodes as visited and adds them to the stack to track the current DFS path. When encountering a node that's already in the stack, a cycle is detected. The starting point of the cycle is identified using the stack index, and the cycle size is calculated as the difference between the stack length and the cycle start. This size is then used to update the max_group variable. Once the DFS completes, the current node is removed from the stack, ensuring that we backtrack properly and continue exploring other parts of the graph. To finalize the solution, we define the calculate_chain_lengths function, which iterates over all nodes and applies the DFS function to unvisited nodes. This ensures that all cycles and chain contributions are identified, even in disconnected graph components. After processing all nodes, the maximum group size is returned as the result. This approach guarantees that we consider every possible group structure, from cycles and chains to special cases like two-node cycles with incoming chains. By combining efficient graph traversal with careful handling of edge cases, the algorithm achieves both accuracy and optimal performance, making it well-suited for the problem's constraints. To solve the problem of determining the maximum number of employees that can be invited to a meeting, we start by defining a Python class called solution with a method maximum_invitations. The input to this method is a list called favorite, which represents each employee's favorite colleague. The first step is to initialize some variables. We calculate the total number of employees, n, and create a visited list to track which employees have been processed. We also define a stack to help with depth-first search, and a depths list to store information about the depth of each node in a potential cycle. Next, we define a helper function called DFS to perform a depth-first search starting from a given employee v. Inside this function, we mark the current employee as visited and add them to the stack. We then find the employee they favor, next_v. If next_v has not been visited, we recursively call DFS on next_v. If next_v is already in the stack, we detect a cycle. The cycle's starting point is determined using the stack's index, and we calculate the cycle's length. We then update the max_cycle variable to store the longest cycle seen so far and record the cycle length for all employees involved. Finally, we remove the current employee from the stack as we backtrack. Outside the helper function, we initialize max_cycle to 0 and iterate through all employees to ensure each one is processed by DFS if they haven't been visited yet. Once all employees have been processed, we shift our focus to identifying special pairs and calculating contributions from chains. A pair is formed when two employees favor each other, meaning favorite, I equals I. To avoid double counting, we only consider pairs where favorite, I. For each such pair, we add 2 to the pair's count and calculate chain contributions for the employees in the pair. The chain contribution for an employee is the depth of their cycle minus 1, which represents the length of the chain leading up to the cycle. We store these contributions in the chain_contributions array. After processing all pairs, we calculate the total _chain_contribution by summing up the values in chain_contributions. Finally, the maximum number of people that can attend the meeting is determined by taking the maximum of the longest cycle, max_cycle, and the sum of pairs and total _chain_contribution. This value is returned as the result of the maximum invitations method. Here, we start by importing the necessary packages and setting up our solution method. The goal of this function is to determine the maximum number of employees that can be invited to a meeting based on their favorite colleague relationships. We begin by defining the size of the input array and initializing two key data structures, a visited array to track which nodes we have processed and a depths array to store the depth of each node in the graph. Additionally, we initialize a variable called max cycle to keep track of the largest cycle detected in the graph. To analyze the graph, we perform a depth-first search on each unvisited node. This is done using a helper method called DFS. The DFS helps us detect cycles and calculate the depth of each node. As part of the process, we also use a stack to maintain the current path during the DFS traversal. This stack will be helpful in identifying cycles. After this, we introduce two other variables, pairs, which will count mutual favorite relationships, and chain contributions, an array that will store the contribution of nodes outside cycles. We'll now proceed to handle these mutual favorite cases and calculate additional contributions. In this portion of the code, we handle the case where two employees are mutual favorites, meaning they favor each other. To ensure we only count each pair once, we check if the mirrored favorite relationship has already been processed by comparing indices. For valid pairs, we increment the pairs variable by 2 because each mutual favorite contributes 2 employees to the meeting. We also calculate and store the chain contributions for these nodes by subtracting 1 from their depths. This step ensures that any additional nodes leading into the cycle or mutual favorite pairs are accounted for. Finally, we calculate the total contribution from all chains using the sum of the chain contributions array. To determine the maximum number of employees that can attend the meeting, we return the greater value between max cycle, which represents the largest cycle detected, and the sum of pairs plus total chain contribution. The DFS method itself is designed to detect cycles and update the depths array. It recursively traverses the graph, marking nodes as visited and detecting cycles using the stack. When a cycle is found, the cycle length is calculated, and the depths of the nodes in that cycle are updated accordingly. This implementation ensures that we accurately account for all possible contributions to the meeting. To solve this problem, we start by analyzing the first example where the input is favorite equals 1, 2, 0. Here, we have 3 employees, so n equals 3. We initialize an array visited to keep track of which nodes have been visited, a stack to simulate the depth-first search process, and depths to store the maximum depth of each node. Additionally, we set self.max_cycle to 0, which will help us track the largest cycle length. The process begins at node 0. Since node 0 isn't visited yet, we mark it as visited, add it to the stack, and proceed to the node it favors, which is node 1. This marks the start of our DFS traversal. Continuing the traversal, we process node 1. We mark node 1 as visited, add it to the stack, and then move to the node it favors, which is node 2. Now at node 2, we repeat the process, mark it as visited, add it to the stack, and follow its favorite, which points back to node 0. At this point, we detect a cycle because node 0 is already in the stack. The cycle length here is 3, so we update self.max_cycle to 3. We then update the depths array for all nodes in the cycle to reflect their participation in this cycle, setting depths equals 3, 3, 3. Finally, we clear the stack by popping all the nodes. Since there are no mutual pairs or additional chains in this example, the total contribution from chains remains 0. Therefore, the maximum meeting size is calculated as the larger of the cycle length and the chain contributions, which gives us an output of 3. Now, let's consider the second example, where favorite equals 1, 0, 3, 2. Here, we have 4 employees, so n equals 4. Just like before, we initialize visited, stack, depths, and self.max_cycle to their respective starting values. First, we detect a mutual pair between nodes 0 and 1 because node 0 favors node 1, and node 1 favors node 0. This adds 2 to the pairs counter, and we also update the depths array to reflect the chain contributions for these nodes, setting depths equals 1, 1, 0, 0. Similarly, we detect another mutual pair between nodes 2 and 3, as node 2 favors node 3, and node 3 favors node 2. This adds another 2 to pairs, bringing the total to 4. the depths array is updated again, resulting in depths equals 1, 1, 1, 1. With all nodes processed, we find that there are no cycles in this example, so self.max_cycle remains 0. The total contribution from chains is also 0 in this case, as there are no additional chains extending from the mutual pairs. The maximum meeting size is therefore calculated as the sum of the mutual pairs in chain contributions, which is 4. This gives us the output of 4. Moving on to the next example, here we analyze a mixed case scenario with the input favorite equals 2, 2, 1, 4, 3. First, we detect a cycle between nodes 1 and 2, as node 1 favors node 2 and node 2 favors node 1. The cycle length is 2, so we update self.max_cycle to 2. The depths array is updated accordingly, with depths equals 0, 2, 2, 0, 0. In addition to the cycle, we also find a mutual pair between nodes 3 and 4, where node 3 favors node 4, and node 4 favors node 3. This adds 2 to the pairs counter, and the depths array is updated to reflect their participation, resulting in depths equals 0, 2, 2, 1, 1. With no additional chains contributing to the meeting size, the total chain contribution remains 0. The maximum meeting size is then calculated as the larger of the cycle length and the sum of mutual pairs in chain contributions, which gives us a value of 2. This concludes the example with an output of 2. To analyze the time complexity of our solution, we need to break it down into the main steps. First, the DFS traversal is used to detect cycles in the graph represented by the favorite array. In this step, each node is visited exactly once, and each edge is traversed exactly once, resulting in a time complexity of O(n), where n is the number of employees or nodes. Within the DFS, there's an operation stack.index, next_v, to locate the start of a cycle when one is detected. While this operation has a complexity of O(k), for a single call, where k is the current size of the stack, we ensure that each node is visited only once during the traversal. Hence, the total contribution of this operation is O(n) across all nodes. Next, cycle length calculation involves updating the depths array for nodes within a detected cycle. Since each cycle node is processed exactly once, this step also contributes O(n) to the overall time complexity. In addition to the DFS traversal and cycle length calculation, we also account for mutual pairs and chain contributions. After completing the DFS process, the algorithm iterates over all nodes again to check for mutual relationships, where favorite, I, == I, and to calculate the contributions of chains extending from cycles. These operations involve a single pass through the favorite array, which adds another O(n) to the overall time complexity. Combining all these steps, the dominant factor remains the DFS traversal and the single pass operations. Therefore, the total time complexity of the solution is O(n). Now, turning to space complexity, the memory usage is primarily determined by the visited array, which tracks whether a node has been visited during DFS. This array has a size of n, contributing O(n) space. Additionally, the stack used during the recursive DFS can grow up to O(n) in the worst case, such as when the graph forms a single long chain. Further contributing to the space complexity are the depths and chain_contributions arrays. The depths array stores either the cycle length or chain depth for each node, requiring O(n) space. Similarly, the chain_contributions array, which holds chain lengths for each node, also has a size of n and contributes O(n) space. Importantly, no additional auxiliary data structures or memory are used beyond these arrays. As a result, the overall space complexity of the algorithm is O(n). When comparing this optimized approach to a brute force solution, the difference is significant. A naive method would involve enumerating all possible subsets of employees to determine valid meeting groups, leading to an exponential time complexity of O(2 to the power of n). By using graph traversal techniques like DFS for cycle detection and chain contribution calculations, the optimized solution reduces the complexity to O(n), demonstrating a substantial improvement in efficiency. Now let's evaluate the algorithm under different scenarios for time and space complexity. In the best case, where the graph contains no cycles or chains, the algorithm still performs a complete DFS traversal of the graph in a single pass through all nodes, resulting in O(n) time complexity. In the worst case, such as when the graph is a single long chain or contains large cycles, the algorithm processes nodes and edges in linear time, maintaining the same O(n) time complexity. For space usage, regardless of the graph structure, the visited, stack, depths, and chain underscore contributions arrays all scale proportionally with the input size, keeping the space complexity at O(n). To mathematically confirm the big O, we note that the DFS ensures each node and edge is visited exactly once, guaranteeing O(n) time. The stack.index operation, although OK for one call, is amortized to O(n), because each node is visited a single time. Additional operations, like updating cycle lengths or calculating chain contributions, are performed in linear passes. Combining all steps, the time complexity is conclusively O(n). When solving problems, one common pitfall is confusing brute force solutions with feasible ones. Brute force approaches, like exploring all possible combinations, can quickly become computationally infeasible as the input size grows. For instance, if you're trying all subsets of size k from a set of n items, the complexity can balloon to O(2 to the power of n, which is impractical for larger values of n, such as n greater than 20. This often leads to timeouts, especially during coding challenges. Another frequent mistake is overlooking edge cases. Scenarios like empty inputs, single elements, or duplicate values are often missed, and these can cause your solution to fail in corner cases. For example, a function might behave unpredictably if given an empty array or an array with only one element. Edge cases are critical because they expose hidden bugs and are commonly tested in interviews to assess the robustness of your solution. Another common error involves using inefficient data structures. For example, relying on an unsorted array for repeated lookups can result in O(n) complexity for each search, whereas a hash map would reduce this to O(1). Choosing the right data structure can significantly improve performance. Similarly, failing to consider problem constraints can lead to missed optimization opportunities. For instance, if the input is sorted, you might optimize your approach using binary search instead of a linear scan. Constraints often provide valuable hints about how you can streamline your solution. Additionally, skipping pre-computation is another frequent oversight. For problems requiring repeated calculations, techniques like memoization or pre-processing, such as building prefix sums, can save significant computation time. Without these optimizations, you may end up recalculating the same values multiple times, unnecessarily increasing the time complexity from O(n) to O(n squared, or worse. In interviews, it's important to focus on key strategies that go beyond just coding the solution. First, pattern recognition is essential. Many problems are variations of well-known techniques, such as sliding window, dynamic programming, or backtracking. Recognizing these patterns can save you time and effort. Clear communication is also vital. Interviewers want to understand your thought process. Even if your initial solution is brute force, explain it logically and show how you refine it step by step. Optimizing early can also set you apart. If you notice opportunities like leveraging sorted input, mention them right away and incorporate the optimization into your plan. Handling constraints proactively is another critical skill. Explicitly discussing edge cases during your explanation shows thoroughness and attention to detail. Finally, always calculate and explain the time and space complexity of your solution. This demonstrates your awareness of efficiency and helps the interviewer gauge the scalability of your approach. To strengthen your understanding, it's helpful to explore related problems that share similar techniques. For example, LeetCode 46 focuses on generating all permutations of a list using backtracking. LeetCode 78 covers generating all subsets of an array, a classic problem that often appears in variations. LeetCode 90 builds on this by introducing duplicate handling and subsets, requiring careful management to avoid redundant results. Lastly, LeetCode 39, Combination Sum, is an excellent example of using backtracking under specific constraints, where you're tasked with finding unique combinations of numbers that sum to a target. These problems not only reinforce key concepts but also provide insight into how slight variations in requirements can influence your approach. Finally, let's explore some alternative approaches and their trade-offs. Backtracking is a powerful technique for exploring valid combinations, especially in problems with constraints, but it can become slow as input size grows. For example, backtracking can be used to prune invalid paths while solving combination problems efficiently. Dynamic programming, or DP, excels when a problem involves overlapping subproblems and requires cumulative results. It can dramatically reduce computation time but often requires additional memory and careful state management. Problems like subset sum optimization are well suited for DP. Greedy algorithms, on the other hand, prioritize speed and simplicity, often achieving time complexities like O(n) or O(n log n). However, they're not always guaranteed to produce optimal solutions for all inputs. Use cases like interval scheduling or minimizing costs showcase where greedy strategies shine. Understanding these trade-offs allows you to choose the most effective approach for each scenario. Thank you for joining this session. We summarized the key points of our solution, discussed important takeaways, and highlighted the efficiency of the chosen approach. Be sure to practice similar problems to strengthen your skills. Don't forget to like, subscribe, and share your thoughts in the comments. See you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!